In this video, we're going to look at transformations of graphs. Transformations means we are moving the graphs, either moving them left or right or up or down. We might be reflecting the graphs over an axis or over a line, or we might be stretching and skewing the original graphs. And so while we get into this, we're first off going to start off looking at a couple of functions and substituting values into the function to formulate tables, because sometimes doing that can help you actually see what's happening once we start making changes to those functions. Then we'll take a look at our parent functions, and then we'll actually look at some situations where graphs are transformed and moved. The first function we're going to look at is f of x is equal to the square root of x. We have some values here for x that we're going to substitute in and solve for f of x. So the first one, and I'm going to do my side work over here in this little cloud. The first one we're going to do is we're going to do f of x when x is equal to 9. So we're going to do f of 9, which is the square root of 9, which is equal to, and we're only going to think about this in the positive values, so we actually have a function. So the answer to that is 3. So we have the point or the coordinate pair 9, 3. Then we're going to do the square root or evaluate the function at x equals 4, which gives us the square root of 4, which is equal to 2. Then we're going to do f of 1, which is equal to the square root of 1, which is 1. F of 0, which equals the square root of 0, which equals 0. And then f of negative 1 is the square root of negative 1. That is actually an imaginary number, so we call that I. It does not live in the real number system, so in this case we're going to take this and we're going to cut it out and say that these give us imaginary answers. And that's okay. We'll talk about imaginary numbers later in the year, so it's important that you know that the definition of I, which is our number that represents imaginary numbers, is that I is equal to the square root of negative 1. But for now, we have some values for our function. Our next function we're going to look at, and again, this is just to make sure we're practicing substituting values into functions and evaluating them and using that to fill out a table, because that's an important skill we might need to use throughout the entire semester. So this symbol right here, I'm going to go over it in red with the little 3 right there. This is actually called our cube root or our cubic root. So if we had something that was cubed to the 3rd power, the inverse of that would be to take the cubic root. They cancel each other out. So if I had, let's say I had x to the 3rd and I was trying to solve, let's say I said y equals x to the 3rd, but I was trying to solve for x, I'd have to take the cubic root on both sides, and that would cancel over here. So x would be equal to the cubic root of y. When it comes down to it, when we evaluate a cubic root, you can actually just say, okay, well, what 3 numbers can I multiply together to get this result? You can also use your scientific calculator to solve for these. You do so by clicking the second button, and then there's a button with a little up arrow. I call it a caret button. It's how you raise a number to a power, but we're trying to do the opposite of that. So if you push second and then the little caret button, it brings you this symbol here. So what you want to do is you want to say whatever root you want first. So I would say, okay, if I want to do the cubic root, I would say 3, second, caret, which will give me this, and then I would put in whatever number I wanted to evaluate, and then I would push enter, and it would tell me and evaluate that cubic root. So we're not going to do that for this one, but you could if you needed to. But again, that is the process. I'm going to erase this area and then we'll solve through and fill out this table. So I'm going to do these quickly. We are evaluating the function at each of these values, so we're just taking the cubic root of each of these. So we end up getting 3 2, 1, 0, -1, because if you think about it, -1 times -1 times -1 is -1. And then this one does not simplify easily, so we could just say the cubic root of -16, or you can evaluate that in your calculator and get a decimal answer. Okay, but again, we're just practicing substituting in values and filling out a table. We can do the same thing for this function. We're looking at, this is called the inverse function, because it's the inverse of the f of x equals x parent function. The inverse is 1 over x. Okay, so here we would just rewrite this. Each of our x values become our denominator, with the numerator being 1. So this one's 1/5, 1/2, 1 over 0, which we've already decided and declared in a previous lesson that we know that this is undefined. Okay, so that won't give us a value, it's undefined. We get -1 and -1 over 6. If I were to substitute in an x value of, let's say, 1/3, I would be doing 1 over 1/3, which is equal to 3. So if I have fractional values, I would end up getting the reciprocal of that value. The reason why we're going over creating these tables is so that when you're asked to graph a function, you know the process for substituting in and finding particular values if you don't automatically know what the function looks like. Because this is always a strategy you can come back to if you need it. If you're given a function and asked to graph it, you can always make a table with the x values and solve for the y values or the function values, and then be able to graph using points. The next important thing to know is our basic parent functions. We call the most simplistic way to represent the different types of functions the parent functions. This means that they haven't been altered or changed at all. It's literally just when the x value is being evaluated as it is with that function and with that operator. So we have, you should be familiar with linear functions. A constant function is when the function is just consistently equal to the same value b. B can be any number. So in this case, this is the function f of x equals 2, because all the outputs on the function are equal to 2. We have the identity function, which is f of x equals x. That's just a line that goes through the origin. Okay. We have our absolute value function, which looks like a V. Absolute value is an operator that tells you the distance from 0. So the absolute value of 6 is equal to 6. The absolute value of -6 is equal to 6. So if you notice, the distance from 0 for 6 is the same as the distance from 0 as -6. And so therefore we both get positive answers, because distance, when we measure distance, it is always a positive value. So in our graph, we see that there are only positive values of y. So it's going from 0 upwards. And that should make sense based on that function. Looking at our other parent functions, we have the quadratic function, f of x equals x squared. That creates what we call a parabola. We have the cubic function, or the cube function, which is f of x equals x to the third, which makes this kind of wavy line. We have the square root function. We have the cubic root function. Now notice for the square root function, we don't get any negative x values. There's none of those included in that function. But in the cubic, we can get negative x values because we can evaluate the cubic root for negative numbers. Then we have our reciprocal function, which we saw as h of x in the previous example, which is f of x equals 1 over x. And that provides this what's called a hyperbola around both sides of the origin. And then we have the square reciprocal function, which is f of x equals 1 over x squared, which, if you notice, the fact that we're dealing again with an x squared means that we have no negative y values when we evaluate our function, because anytime a number is squared, we only get a positive result. So these are all of our parent functions. It's really important to see and know them. I mean, sometimes in classes, you might be asked to make like flashcards of these so that you know which parent function goes with which equation, and which graph goes with each function. And then it's also important to know what the parent function looks like, because if you learn and understand the rules for transforming these, then you can actually just take that parent function and shift it or reflect it around as you need it. So I'm going to wrap up part 1 of these notes now because it's only about a 10-minute video, but we're going to continue with part 2. So make sure you watch the part 2 of Transformations of Functions video.